Let's take a look now at linear equations in two variables. Oftentimes, whenever you look at a linear equation, it involves a single variable. Something like 2x plus 7 is equal to, let's say, 17. Okay? In this case, you have a single solution to your linear equation because you can isolate your variable x. So here you can subtract 7 off from both sides, minus 7 to both sides. 7 minus 7 is 0, leaving you just your 2x. And 17 minus 7 gives you 10. Then you can divide both sides by the coefficient here. 2 divides 2 to give me 1x. And 10 divided by 2 gives me 5. So here I have a single solution. Okay. If you want to write this as a solution set, you write that as a set with the solution inside. Okay. That doesn't look particularly different. It doesn't look particularly useful to write it one way or another. They're just different notations. So here this is a single solution, whereas this would be your solution set. It would be a set with the solution inside. But that's not the only way a linear equation can look. This is a linear equation in one variable. If you include a second variable, for example, x and y at the same time, that will give us a linear, let me write it off to the side so they look the same. That would be a linear equation in two variables. And that would be something like 2x plus 3y equals to 12. Notice that you have two different variables. Because you have two different variables, isolating one doesn't give you a solution. If you isolate x, that's going to move everything over this way, including your y. So you have x is equal to some expression that involves y. But since you don't know what y is, you don't really know what x is either, at least not right away. So when we talk about linear equations in two variables, we're going to find solutions, but not exactly the same way as we do with one variable. Okay? So first of all, we need to talk about what we mean by solutions. We know that for a one variable equation, you have your solution is the value of x. Well, for a multiple variable equation, you're going to have solutions that involve a value for each of these. You're going to have to find out what x is and what y is. Notice that's not two different answers. That's part of the same answer. So for example, right here, I could say, and for right now, we're not going to talk about how to find them. We're just going to talk about defining what we mean by solutions. We'll talk about how to find those in a few moments. Let's say you have x is equal to 6 and y is equal to 0. Notice that is a solution, because if you plug in 6 right there, 2 times 6 is 12. Plug in 0, 3 times 0 is 0. And 12 plus 0 is 12. So this works as a solution. Notice this is not two solutions, it's one solution. But that one solution involves two different values. I could find another solution though. For example, I could say x is equal to 3 and I could say y is equal to 2. And that works because 3 times 2 is 6. And 2 times 3 is also 6. And 6 plus 6 would give us 12. And I could find yet another solution. I could say, for example, x is equal to negative 6, and I could say y is equal to positive 8. And that works because 2 times negative 6, that would be negative 12, and 3 times 8, that would be 24, and 24 and negative 12 give us 12. And notice that's another solution. The difference between this problem and this problem is, even though you have just one extra variable, you notice that you have more solutions. And here, this isn't all of them. We could keep looking for more and finding more. Okay, so what do I do? How do I write this? When I have just one solution, I just write that solution, x equals to 5. But if I have these solutions like this and they keep going, what do I do? So first of all, for convenience, we know that when we have the two numbers, one represents x and one represents y. So we generally don't write the two variables. When we write a solution, we write it as an ordered pair. Now remember, when you write an ordered pair, the first coordinate represents your x value, and your second represents your y value. So here, instead of saying x equals to 6 and y equals to 0, we can say just 6, 0. Likewise, we can say 3, 2, and we can say negative 6, 8, like that. Now, the other problem is, if I have more solutions than this, how do I find them all? I mean, do I really need to go through and just start listing solution after solution? Well, no. And in fact, the way we've written it here suggests the better way to organize this information. When you have just one solution to find, you find it and you're done. However, when you have multiple solutions that you're going to need to find, with a linear equation in 2 variables, you'll have lots of solutions that are ordered pairs, right? They're all going to be ordered pairs. But because they're ordered pairs, that means we can graph them. And because the graph allows you to summarize a lot of information all at the same time, it'll be useful to use a graph rather than to list the solutions the way you normally would for an equation of 1 variable. So using this exact same equation, let me go ahead and graph what these solutions look like. My favorite ruler. I've got it as a gift years and years and years ago. It's a bunch of ice creams. They're adorable, aren't they? Look, this one's even smiling. This one stopped smiling because someone bit it. I guess it wasn't happy with being bitten. So in any event, all right. So I have, well, let me go ahead and put some tally marks on here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm just going to write every, I'm not going to write every one just because I don't want it to be all cluttered up. And over here, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, negative 5, 6, and so forth like that. So now I can go and graph each of these points. 6, 0 means go 6 in the direction of x. Remember, x is horizontal, y is vertical. So 6 steps this way, 1, 2, 3, 4, 5, 6. And then since your y is 0, that means don't go up or down. Just go ahead and stay right there at 6, 0. Okay. This solution, 3, 2. All right, well, that's 3 to the right, 1, 2, 3. And then your second coordinate is positive, so you're going to go up by 2. And there we go. And then I had another solution over here, negative 6, 8. Since x is negative, that means I'm going to go to the left. 1, 2, 3, 4, 5, 6. And I'm going to go up 8. 1, 2, 3, 4, 5, 6, 7, 8. And it looks like I ran out of space there a little bit, but close enough, like that. Now, notice that these points fall in a pattern. When I have these solutions listed out as a list, okay, well, I have some solutions, but it's hard to tell any pattern from just a list of numbers. However, if you look at it visually through a graph, you notice that all of these points fall on the same straight line. So when we solve a linear equation in 2 variables, writing the solutions explicitly as a collection of points would take a very long time, and it doesn't give you the pattern. But by graphing those solutions, we start to note that our solutions all lay on the same straight line. But it's more than just that. It's more than just saying, oh, the solutions happen to lay on the same straight line. Because notice that there are other points on this line besides the 3 that I just found. For example, here's a point. What would that one be? You're not going left or right. You're just going to go up 4 steps. So that would be the point, what, 0, 4? Notice that I never found this point as a solution. I didn't do any computation or anything. All I did was I found it on my line. But look what happens when I take these 2 numbers and plug them in. 2 times 0 is 0. 3 times 4 is 12. And 0 plus 12 is 12. That works. This point is a solution. So it's not just that, oh, if I find solutions, they're all on the same straight line. It turns out that even if you don't find them explicitly, just by creating this line, every point on this line serves as a solution to this equation. I do that one more time. Let's see here. Here's a point. That looks like it's 3 steps to the left and 6 steps up. So that's going to be what? -3, comma 6. And notice, again, that wasn't one of the solutions that we had before. It's just some point that we picked out of the line. But I can fairly confidently say that it's going to work. -3 times 2, that's -6. 6 times 3, that's 18. And -6 plus 18, sure enough, that's 12. So by creating this line, we not only summarize the points that we find, but we, without any extra work, manage to find other solutions because all the points on this line will work as well. So let's go ahead and do that from scratch. Let's go ahead and actually find out how to do that. Because right here, I gave you some solutions. I gave you 3 solutions, and from that we graphed a line, and then that line allowed us to find other solutions. But how did I graph these in the first place? Okay, so let's go ahead and do that. We're going to graph the equation. Normally we would say solve, but in this case finding individual solutions is not as useful as creating a graph. So really the full instructions should be find solutions, graph them. Find solutions and graph them. But that's a lot to say, right? So usually we just say graph. All right, so let's go ahead and graph. And I'll do one that's similar to the one we just had. I'm going to go ahead and graph 3x minus, let's say 2y is equal to 12. It's not exactly the same, but it's similar. All right. Okay, so first of all, in order to graph this line, I'm going to need to find some solutions. Okay, how many do I need? Turns out I only need 2. Okay, why 2? Because what we're graphing here is a linear equation in 2 variables. What tells you it's a linear equation is that the variables don't have any exponents. Or if you like, you can say they have an exponent of 1. Right? X to the first and y to the first. When your variables have other powers, power 2, power 3, power 4, or if they have any roots, like a square root, then that's not a linear equation. But when all you have is x and y, and the only thing you're doing to those x's and y's are either adding or subtracting or maybe multiplying or dividing by a number, that's going to give you a linear equation. Whenever you have a linear equation, the graph will be, surprise, surprise, a straight line. That's one reason we call them linear equations, because their graph is a straight line. So here, note, linear equations, the ones that the variables have power of 1, x to the 1, y to the 1, linear equations graph as straight lines. Mathematicians are not particularly inventive when it comes to naming stuff. We try to name stuff in the most obvious way possible. If someone took the time to call this a linear equation, it has something to do with lines. In this case, the graph is a straight line. The nice thing about straight lines is that you only need 2 points to graph them. Because if I tell you, here's a single point, and a straight line passes through that point, well, I don't know if it's that line or that line or that line or that line. There's lots of straight lines which pass through that point. However, if I give you 2 points and tell you a single straight line passes through both of those points, there's only one line that does that. So if you can find 2 solutions, that's enough to graph the line. But once you have the line, that will represent all of your other solutions, even if you didn't actually go through and find them. So how do we find our individual solutions? There's a few ways to do that. Right now we're going to start off with the simplest way, and that's by simply substituting in a value for one of your variables. It doesn't even matter which one you substitute. So what I'm going to do is I'm going to say, okay, I need to find an x and a y. What I'm going to do is I'm going to pick a number to plug in for x. It's arbitrary. I can choose whatever number I like. Because what I'm going to do is once I substitute that number in, I'm going to solve for y. Now, although you can substitute any number you like, it's completely arbitrary, you're probably better off using simple numbers. Yes, you can use 4,916,000. That's going to make your arithmetic harder. Yes, you can use 7/8, but that's going to make your arithmetic harder. Yes, you can use pi, but that's going to make your arithmetic harder. The simplest thing to do is to choose small, simple, and easy to handle numbers. Something like 0, or 1, or 2, or 3. Something small and simple to work with. Right? So let's see what happens if I plug in x is equal to 0. Let me do that down here. If I set x equal to 0, and remember, this is arbitrary. I chose whatever number I wanted, keeping in mind that I want to use something simple. Let's see what happens to my equation. If I set x equals to 0, then that's going to tell us that 3 times 0 minus 2y equals to 12. Okay, well, 3 times 0 is 0, so I can just ignore that. That's just going to give me minus 2y equals to 12. And if I now divide both sides by a negative 2, that isolates my y variable. Y is equal to 12 divided by negative 2. A positive divided by a negative is a negative 6. And there we go. That's my y value, negative 6. That is the solution. Keep in mind, the solution is the entire thing. It's not just one of the numbers. It's x comma y. We can do this with any value here, but again, keep in mind you want to use small, simple numbers. I could say 1, 2, 3, 4, 5. Incidentally, I could plug in a number for y. I don't have to plug it in for x. I could say, let me plug in y is equal to, for example, 0. Right? I already said x equals to 0, but I haven't done y equals to 0 yet. I could say y is equal to 1, or 2, or 3, or 4, or 5, or any number I like. So that really is a free choice. You're going to pick one variable, doesn't really matter which one, and you're going to plug in some number. Again, doesn't matter which one, but you want to choose something simple. Here, I'm going to say x is equal, let me go and plug in for y. I'll plug in y is equal to, I don't know. I want to keep it simple, so I'll use 0 again. Let me set y equal to 0. Okay, well then that's going to be 3x minus 2 times 0 is equal to 12. I plug in y is equal to 0. 2 times 0 is 0, so I can just make that we don't worry about that anymore. We're left with just 3x equals to 12. And now to isolate our x, we can divide both sides by 3, and that isolates our x. We have x is equal to 12 divided by 3 is the number 4. So if I set y equal to 0, that gives me x must equal to 4. And I can keep doing this. I could pick other numbers. I could say, okay, let's set x equal to 2 now and figure out what happens to y. Or I could say let y equal to 6 and let's figure out what happens to x. But we have 2 points, and that's really all we need. So now let's go ahead and graph this. Let's see here. That's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Let's make that negative 5. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. Okay. And the reason I'm going up to 6 is because that's the biggest number that I have here, or negative 6. If I had bigger numbers that I needed to graph, well, then I would make my graph a little bit bigger. All right, so I have one solution, 0, negative 6. That means don't go left or right at all, but go down 6 steps. 1, 2, 3, 4, 5, 6, right there. And then I have, let's see, 4, comma 0. That means go 4 to the right. 1, 2, 3, 4, and then don't go up or down at all. I have 2 points, which is now sufficient to graph my equation. And there it is. Note that we only took the time to graph 2 points. If you graph 3, 4, or 5, that's fine, but it doesn't give you any more information because all of those points will lie on the same straight line. The nice thing about this is that it does give you information for free, meaning without having to do any more arithmetic or any more algebra, the graph itself gives us more solutions that we haven't found yet. For example, here is a point. 2 to the right, and down 1, 2, 3. Okay. Here I didn't want to use 1 because if I go right by 1, I'm going to go down. Notice that's a little bit past 4. It's going to be a fraction, 4 point something. And since my graph is drawn freehand, I didn't use any graph paper or anything, it'll be hard to tell. So here I chose this one because here it's actually a whole number. Right? You can use the graph to get more precise, but you would have to actually be very careful when graphing it. But in any event, here this one works nicely as a whole number. 2 to the right, down 1, 2, 3, and that's 2 comma negative 3. Notice I never actually did the algebra or the arithmetic to find that solution, but it works. Look, 3 times 2, that's 6. Negative 2 times negative 3, that's positive 6. So you have a 6 and another positive 6, which gives me 12. So, sure enough, that one works. And if you took the time to find other points that are on this line, just go through and try to find points that you recognize. They're all going to be solutions as well. So by just finding 2 solutions, all the rest are automatically filled in. Okay. Go ahead and give this a try. Let's have you graph the equation 3x, let me make that a minus 3x plus 5y equals to, let's say 30. You're going to find at least 2 solutions. If you want to find more, you can, but only 2 are really necessary. You're going to find at least 2 solutions and then graph. Keep in mind, you can substitute any numbers you like, but you probably want to keep things simple by using small, simple numbers. As 0, 1, 2, negative 1, something like that. All right. So go ahead and pause the video, give that a try, and once you have your graph, you can unpause and we'll confirm that together. All right, so let's give this a try. We want to find at least 2 solutions. We want to find for each of those solutions, we want to find an x and a y, and we're going to go ahead and substitute in some values. Here, I'm going to just use, let's say 0 and, well, let's just start with that. So I'm going to set x equal to 0. You'll notice that I like 0 because that's a fairly simple number to work with. If I make one of my variables 0, that means that term just goes away. Now, you don't have to use 0, but it is fairly convenient. So let's go ahead and do that. I'm going to go ahead and set x equal to 0. All right, well, if I do that, that's going to give me negative 3 times 0 plus 5y equals to 30. Okay. Well, then that's just 0. That goes away. So I can just write that as 5y equals to 30. Okay. So now, if I want that y by itself, I need to divide both sides by 5. If I divide this by 5, it gives me just y. If I divide this by 5, it gives me 6. So there we go. That's one solution. If I set x equal to 0, y is equal to 6. All right. So now I need a second solution. I can plug in whatever number I like, and again, I can substitute in for x or for y. Now keep in mind, you don't necessarily have to get a nice number like this. Here, when I set x equal to 0, I get y is equal to 6, which is a nice whole number. There's nothing that says that it has to be that way. If you pick the wrong number, and really it's not a wrong number, there's nothing wrong with it, but if you pick a number that doesn't necessarily work nicely in this equation, you might get a funny looking answer. There's nothing wrong with that, by the way. So here, let me pick one that's not going to give us the nicest result. And here, let me just pick x equals to 1. Okay. So, what does that do? All right, negative 3 times 1 plus 5y, that's going to equal to 30. Now, negative 3 times 1 doesn't just go away. It's negative 3. So that's going to be negative 3 plus 5y equals to 30. I can add the 3 over to this side. So that'll give me 5y equals to 33. I have to add 3 to make this go away. But whatever I do to one side, I do to the other side. So 30 plus the extra 3 is 33. And finally, I can divide both sides by 5. If I divide this by 5, it gives me just y. If I divide this by 5, well, that's 33 over 5. Notice that's not a nice whole number. I can leave that as a fraction if I want. Or I can go through and do the division and get a decimal. 33 divided by 5. Let's see, 5 goes into 36 times. 6 times 5 is 30, with a remainder of 3. Drop a 0. 5 goes into 30 6 times. 6 times 5 is 30. And then you have no remainder. Pick your decimal straight up to give you 6.6. So over here I can say x is equal to 1 and y is equal to, I can leave that as a fraction or I can convert it to a decimal. Either one's fine. Or you can even use a mixed number if you want. So notice that again, your answers aren't always going to be nice whole numbers, and that's okay. Now, if you just don't like numbers like this, then what you can do is you can just pick another number. You can say, oh, wait a minute, that's not going to give me a nice whole number. Try something else. Maybe I can try y is equal to 0. Or maybe I can try y is equal to 10 or something like that. So there's nothing wrong with a solution like this. 1 comma 6.6 is perfectly acceptable, but you're free to choose something else if you like. What's important is we have a couple of solutions. So now we can graph. One, 2, 3, 4, 5, 6, 7, 8. Let's see, that's our 5 right there. 1, 2, 3, 4, 5, 6, 7, 8. So that's our negative 5 there. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. All right, so let's see here. We have 0, 6, which means from the origin. Don't go left to right because of the 0. But then the 6 tells you to go up 6 steps. And that puts you on the x-axis right about there. Okay. Now, 1 comma 6.6, that means go to the right by 1 and go up 6 and a little bit more. Notice you don't go all the way to 7. This is 6, this is 7. 6.6 would be a little bit past halfway. So right around there. Okay. Note that I didn't actually take the time to measure this perfectly. I'm not using graph paper. For now, we're just learning how to sketch these graphs. We're not looking for high precision, but we do need to know where our points are, and we do need to have at least a sketch of a graph. But notice that even though that's not perfect, I didn't actually take a caliper or a ruler and measure it out perfectly, it is about the right place. Right? 1 to the right and up 6. Right here, 6 is at the line, and up a little bit more. So now that's all we need. We have our 2 points, which we can now connect and get our result. Let's see here. And there's our result. You'll note that if you use a different point, if you use different numbers, if, for example, you had said x is equal to 0 and y is equal to 0, or if you happen to have said x is equal to 1 and y is equal to 5, or if you had said x is equal to 0 and y is equal, and x is equal to 8, if you had chosen different numbers, you would get different points along this line. But no matter what, all of us should get this exact same line. The one that crosses up here at 0, 6, and that goes up this way. Now, that being said, it is often useful to use the number 0 for 2 reasons. One, this will give us an easy to find solution, because when x is equal to 0, one of your variables goes away. Or if y was equal to 0, well, then your other variable would go away. Right? Which makes what is left over much simpler to deal with. But the other reason we want to do that is because it gives us a very key piece of information on the graph, something that's easy to find, easy to interpret, and easy to visualize. So let's do another problem like this. I'm going to go ahead and graph, let's say 3x minus, let's say 7y is equal to 42, because why not? Right? Now, I'm free to choose whatever numbers I like. I can say x is equal to 0, 1, 2, 3, 4, 5, or whatever. And I can say y is equal to anything I like. But what I'm going to do is I'm going to choose 0 for both of them. If I say x is equal to 0, let's see what happens. And then separately, if y is equal to 0, let's see what happens. So this will give us two different solutions, 0 comma something and something comma 0. All right. If we set x is equal to 0, what that's going to give us is 3 times 0 minus 7y equals 42. Since 3 times 0 is 0, I don't have to worry about that number anymore. I can just ignore that. And now if I divide both sides by negative 7, if I divide this by negative 7, it gets me my y all by itself. If I divide this side by negative 7, positive divided by a negative is a negative. 42 divided by 7 is 6. So that's going to be a minus 6. If I now do that for the other variable, I can say set y equal to 0. Well, that's going to give me 3x minus 7 times 0. That's equal to 42. Since 7 times 0 is 0, I can safely ignore that number. It gives me 42. And now, if I divide this by 3, that'll give me my x. But whatever I do to one side, I do to the other side. Dividing this by 3 will give me 14. So that's my other solution, 14 comma 0. One thing to take away from this is, of course, it's much simpler to work with because once one of your variables is 0, you have to worry about the remaining one. There's no extra constants to worry about. But on the graph, you'll see something else of note. Okay. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. My y values, let's do 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right. We can plot these points. 0 comma negative 6 means don't go left or right, but go down 6 steps to this point here. 14 comma 0 means go 14 to the right, and then don't go up or down at all. Just stay right there on the x-axis. Notice that by graphing these 2 points, you find where these graphs hit the 2 axes. You find the point where your graph is going to cross the x-axis and the y-axis. This is visually nice. It gives you a nice anchor point that tells you, okay, here is exactly where this point is. I don't have to go up here and find it. I don't have to count off or anything. It's right on the axis. So it makes it visually simpler to deal with. But also, when we start looking at applications of math, when we start looking at linear equations and doing things with them, oftentimes what we're going to be looking for is what happens when your graph crosses either the x-axis or the y-axis. These have applications outside of math in chemistry, in biology, in economics, in physics, in, believe it or not, in psychology and sociology, because when we deal with the social sciences, we often deal with statistics, or in other words, more math. So we have these 2 points that are not just visually simple to work with, not just arithmetically simple to work with, but are also useful in applications. Because of that, these 2 points are often found, they're often more often used than any other point, and they're used so often that they have a name. These are called the intercepts, because they're where the graph crosses, where it intercepts one of the axes. This is where your graph crosses, where it intercepts the x-axis, so it's called the x-intercept. Okay. Note that the x-intercept is a point, which means it has a coordinate. It's not just the number 14. It's actually 0 comma 14. Oh, I said that backwards. The 14 should go first, right? 14 comma 0. Right? The intercept is a point. It's not just a number. So you have 14 comma 0. Note the way we found the x-intercept was by setting y equal to 0. You find by setting y equal to 0. So that means your x-intercept will always look like some number comma 0 because the y will be 0. It doesn't take any imagination to realize that this is called the y-intercept because it crosses the y-axis. This one, the x-intercept because it crosses the x-axis. Then this one is called the y-intercept because it crosses the y-axis. I'm getting ahead of myself, right? So this is where you cross the x-axis. You call it the x-intercept. This is where you cross the y-axis, so you call it the y-intercept. Again, it's a point, not a number. So you have x comma y. Your y-intercept is not just -6. It's 0 comma -6. It's a point. It has two parts, an x and a y. And the way you find that is, well, right here we found that by setting x equal to 0. That was our first step. Find by setting x equal to 0. So that means that your intercept will always look like 0 comma something. Your y-intercept will be 0 comma something. All right, so go ahead and give this a try. Take the following equation and graph it. You're going to graph it and you're going to label the intercepts. Since you need 2 points to graph anyway, you might actually just want to graph the 2 intercepts and do everything at the same time. All right, so you're going to go ahead and graph and label, and when we say label, when you give the points, 0 comma 5, 12 comma 0 or whatever, and go ahead and so you're going to graph and label the intercepts of the following linear equation in 2 variables. Let's go with 5x. Oh, let's see here, 5x minus 2y equals to negative 20. Okay, so go ahead and give that a try. Go ahead and graph this, and while you're graphing it, go ahead and label the intercepts. If you want to find the intercepts and use those to graph, that would make things just slightly shorter. But if you want to just graph first and then worry about the intercepts, that's fine too. Pause the video, and once you are done, go ahead and unpause and we'll go through it together. All right, so let's take a look. To find the intercepts, we're going to find 2 points that are solutions to this equation anyway. So by finding the intercepts first, the graph will be automatic. So let's go ahead and do that. I'm going to take my x, I'm going to set it equal to 0. I'm going to take my y, and I'll set that equal to 0. And now I have 0 comma something for my y-intercept and something comma 0 for my x-intercept. So now I just need to find what those are. I'm going to go ahead and set x equal to 0. Remember, that's my y-intercept. Right, so x equals to 0. So that's going to give me 5 times 0 minus 2y equals negative 20. 5 times 0 is 0, so that goes away. It leaves me just my minus 2y equals minus 20. And then if I divide both sides by negative 2, this gives me just my y. If I divide negative 20 by negative 2, the negatives divided by a negative gives me a positive. 20 divided by 2 must be 10. So there we go. There's my point. 0 comma 10. And this is my y-intercept. I can do the same thing by setting y equal to 0 to help find my x-intercept. Let's see, that's going to be 5x minus 2 times 0 equals negative 20. Okay. Anything times 0 is 0, so I can just, that goes away. That's going to give me 5x equals negative 20. So now I can divide both sides by 5. 5 divided by 5, that's just the number 1, which is what I want. I want 1x. If I divide negative 20 by a positive 5, negative divided by a positive is a negative. 20 divided by 5 is 4. So that is my x-intercept, negative 4 comma 0. So I'm supposed to label these, right? Well, let me label them on the graph. All right, so let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see, that's 5 and 10. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so I have 0, 10 as my x-intercept. Notice that, 0, 10 is my y-intercept. Notice that that crosses my y-axis the way it's supposed to. And then here, negative 4 comma 0, that would be negative 4 along the x-axis. That'd be 4 steps to the left. Don't go up or down at all. That's where you cross the x-axis. So that's my x-intercept. So here, I'm going to go ahead and label those. This is negative 4 comma 0. That's my x-intercept because it's on the x-axis. You'll often abbreviate intercept as int, intercept. That's mostly just because intercept is a long word to write, and we don't want to take up so much space. If you write out the full word, that's fine. Here, this is 0 comma 10, and this is my y-intercept, and you'll often see it abbreviated in many books as y-int. And now you have your two intercepts. Now, you were supposed to graph the equation too, but remember the intercepts are themselves solutions to your equation, so without doing any extra work, you're done. Because those solutions are included, and so your line must pass through them. So there we go. Here's our graph along with the two intercepts that we've labeled. Finally, when graphing linear equations of two variables, there are two special cases, which, although they are technically linear equations, they do look a little different. They're not particularly more complicated, but they don't look exactly like this. So far, every graph we've seen has been a line that's slanted, either slanted from lower left to upper right, like these, lower left to upper right, or from upper right to lower left. Either way, they're slanted, like these. But there is the possibility that your graphs are not slanted. They're either perfectly vertical, straight up and down, or perfectly horizontal, left to right, flat. The equations that give those graphs are actually simpler than the equations of the graphs we've been seeing. So for example, let's say we're going to graph an equation like this. X equals to 3. Now you say, well, that's not two variables, right? Because it's just an x. Well, that's sort of true. But you could think of this as 1x plus 0y is equal to 3. That means the same thing, right? 1x, there's no y's, and that's equal to 3. But by writing it this way, it becomes apparent that you're thinking about it as a linear equation. Here, normally our linear equations are things like 1, 2, 3, 4, 5, you know. Over here, we use 0 and 1. But it still technically qualifies. So what does this graph look like? Well, think about what it says. It's saying we don't care what y is, because y can be whatever number. Since you're multiplying it times 0, it's going to be 0 anyway. So here, all that matters is x. Solutions to this type of equation look like this. X is equal to 3 and y is equal to 0. That works because here, x is equal to 0. X is equal to 3. We don't care what y is. You could say 3 comma 1, because again, x is equal to 3 and we don't care what y is. We could say 3 comma 2. We could say 3 comma 17. All of those work just fine because again, x is equal to 3. Y can be whatever we want. Doesn't matter. So if you go through and graph that, look what that looks like. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 3, 0. Well, that's that point right there. 3 to the right, and then you don't go up or down at all. 3 to the right, up 1. 3 to the right, up 2. 3 to the right, up 17. Or really any other point. Because as long as x is equal to 3, your y value can be as high or as low as you want. But what's the shape of that line? Rather, what's the shape of that graph? It's a vertical line, straight up and down. So whenever you have an equation that looks like x equals to a number, that's going to be a vertical line. Note, x equals to a number, and here it doesn't really matter what that number is. X equals to a number, that gives you a vertical line. A horizontal line is the graph of something that looks like y equals to a number. So for example, if we were to graph y equals to, let's say, -2, again, my solutions, I don't care what x is, because there's no x in this equation. So x can be 0 or 1 or 2 or 3 or anything else. As long as y is -2, that's going to work as a solution. But if I go through and graph something that looks like that, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 2, 3, 4, and 5. If I go through and graph that, 0, -2, that would be down here. Don't go left to right, down by 2. Right by 1, down by 2. Right by 2, down by 2. Right by 3, down by 2. Notice all of these line up along the same horizontal line. Notice since this graph never crosses, this graph up here, it never crosses the y-axis, that means there is no y-intercept. Most graphs have both an x and a y-intercept. However, a vertical line may not have a y-intercept. So here, this does not have a y-intercept. Unless, of course, the line itself was the y-axis. If you had something like x equals to 0, well, then it crosses the y-axis at every point. But that's not generally what we mean by a y-intercept. Usually we're looking for just a single point. Likewise over here, let's make a note of this. If you have something like y equals to a number, and again, it doesn't really matter what that number is, your graph will be a horizontal line. So this graphs as a horizontal line, a flat line. And again, note this one does not cross the x-axis. It crosses the y-axis right there, but it never crosses the x-axis. So here there is no x-intercept. Does not have an x-intercept. Okay. And there we go. So that brings us to the end of our discussion for today. If anybody has any questions, comments, or problems, please make a note of those, reach out, and I hope everyone has a nice day.